Hey guys, today we're going to be looking at nuclear chemistry. We're going to be looking at 3 different types of nuclear reactions and their corresponding equations. But before we can get into that, we need to review isotopic notation, which we learned way back in, I think, Unit 2. So isotopic notation was where you have the symbol of an element, like here, U is uranium, and at the top you have the mass number, which is protons plus neutrons. And on the bottom, you have the atomic number. And you can find the atomic number for an element by looking it up on the periodic table. If you look up U on the periodic table, you'll see that it is uranium, which is element number 92. So on the bottom here, you put that 92, which is the atomic number, or the number of protons. And there are 4 types of decay that we're going to be talking about. There's going to be alpha and beta decay. Those are going to be for regular, plus we're going to look at gamma emission. And then also for pre-AP, we're going to have some electron capture and positron emission. Now those are going to be in a separate video that is done by Ms. Rigsby. So if you're pre-AP, watch through this one and then watch through the one that's separate about electron capture and positron emission. All right, first up is alpha decay. So alpha decay happens when you have a helium nucleus that is emitted from a regular nucleus. So our example here is going to take uranium-238. And this little question mark thing is supposed to be a decay symbol, which is just the arrow. So we're going to take that uranium-238 and it's going to turn into helium plus something else. Now we know mass has to be conserved. However many things you start with, you have to end with. So we have to balance out the number of nucleons, which is the mass number on the top. So we have 238 on the left. Right now we have got 4 on the right, which means we need 234 more to account for all of them. So we're going to have a mass number for our remaining substance as 234, or our remaining nucleus. And then you've got to do the same thing with the number of protons. On the bottom, you've got 92 protons for uranium. Helium takes 2 of them, which leaves 90 left over. And if you go look at 90 on the periodic table, that is the element thorium, which is TH. Already represented for you there. Beta decay is a little bit trickier. Beta decay ejects an electron from the nucleus, which is weird because the electrons don't stay in the nucleus. They reside in the electron cloud around the nucleus. So what actually happens is one of the neutrons from the nucleus, it turns into or decays into a proton and an electron. So the neutron goes away, makes a proton and an electron. So the total number of mass doesn't change because the neutron just becomes a proton with the same mass. So our top number does not change at all. We'll have 131 on the other side, which makes sense because our beta particle that we're emitting has very, very little mass because electrons are so tiny. But the protons are going to be a little bit different. We've got 53 protons for iodine. You can find that by looking it up on the periodic table. And then this -1 means we're subtracting a -1, or we're making this side balance out with -1 to 53. So if you subtract a -1, that's the same as adding 1, and you get 54. And 54 minus 1 is 53, so your sides here are balanced. And if you look at element 54, that is xenon. So in the beta decay of iodine 131, you're going to end up with xenon 131. It just goes up 1 element. All right, and last thing is gamma ray emission. So after decay, the nucleus gets pretty unstable because it just split or it just turned a neutron into a proton. So it will emit some radiation in the form of light, or gamma rays, which is a type of electromagnetic radiation akin to light. And so it's going to emit that radiation. If we are writing this in equation form, it'd be something like, let's see, iodine 13153, if we're going to steal the one from above, yields our gamma particle, which has no mass and no protons because it's just energy, but it leaves the nucleus the same, just a little bit less energetic. So our equation with gamma rays just yields the exact same element with the same mass number and the same number of protons. All right, if you're regular, go work on your practice that covers this stuff, alpha and beta and gamma decays. If you are pre-AP, go watch Ms. Rigsby's video over positron emission and electron capture.